Hello everyone. Today in this lecture 3 of module 1 we are going to discuss about the canonical and polar representation. So before getting into the canonical representation, you'll have an idea of what is meant by this canonical. It's like we are trying to narrow this whatever the data is there, we are like making it a narrow band. So canon is like that only. It's like what is a ಹಳೆ ರಾಜರ ಹತ್ರ ಒಂದು ತೋಪು ಅದು ಇದು ಅಂತ ಹೇಳ್ತೀವಿ. So that is like that. Canon is like that only. Okay, it's like a canon where we'll be passing on the data with a set of a what you call as a band set to one certain frequency. And what the polar representation, the polar is like we are representing the complex form into the polar is what we have on magnitude and which is having a angle there. So we represent it like 25 at the at the and some angle, for example 30 degree, 40 degree or 0 degree. So we can say that's with a phase shift regarding that. So how we represent this data in the terms of the Hilbert transform in the canonical and polar representation. The earlier we saw it in terms of envelopes, the different pre-envelopes and the complex envelope, of where we discuss about the representation of the data of the Hilbert transform in terms of a positive frequency, negative frequency, and the complex forms. Now that we try to modify and we get into the canonical form, the angle of the phase shifts. So we'll be looking into those things. So first we'll look into the band pass signals of the canonical representation. As for the definition, the real part of the pre-envelope S plus of t is equal to the original band pass signal S of t, and it can be expressed in terms of its complex envelope S cap of t, as S of t is equal to real part of S cap of t into e raised to j 2 pi fct. So this is the equation what we are trying to say. As S of t we are representing the canonical one. So here we take only the real part. Since S cap of t is a complex value quantity, it can be expressed as S cap of t is equals to Si of t plus j into Sq of t. Okay, this is nothing but the Cartesian form. So this Cartesian form is nothing but we consist of two parts here. One is the in-phase component, another is the contrast-phase component, and both are real valued low pass functions. Both are real valued low pass functions there. And this equation 9. This equation 9 is what we have derived in our previous video. That is, we have got the this part we have got it in the complex envelope. So from there, the complex envelope, we can get the real part of this. But what is the S cap of t? We have represented in the Cartesian form. Where Cartesian form is again consists of the in-phase component and the quadrature phase component. So now if we take the equation 9 and we can implement this or substitute this equation 10 into it, we get in terms of a like this way, that is S of t is equals to a real part of S cap of t is nothing but Si of t plus j Sq of t, that we have substituted here, and e raised to j 2 pi fct, that is nothing but cos 2 pi fct plus j into sin 2 pi fct. That is the real part is what we can represent. So when we multiply here, I can get like this way, Si of t into cos 2 pi fct, and so here one term is missing here, it should be a j here. Okay, then Sq of t plus j sin 2 pi fct. So j and j will multiply and get me the value of the square root of minus 1, the whole square will become minus 1, so it will become Sq of t into sine 2 pi fct, and that minus sign will be denoted here. Then again si of t plus, so in si of t cos 2 pi fct, that is now si of t plus j sin 2 pi fct, which will be like here. It's nothing, we don't have any j term here, one term will come here, next plus j sq of t into cos 2 pi fct. So this term will come here. So this is, we have arranged in terms of a real part and the imaginary part here. When we consider only the real part of this signal, s of t will become si of t plus into cos 2 pi fct minus sq of t into sin 2 pi fct. That will be equation 11. So this is equation 11. Now here again we classify here into the two components. So that is trying to say that, so when we consider real part and when we consider imaginary part, there have two parts there also. The in-phase component and the quadrature phase component in the real part, and in imaginary also we have a quadrature phase component and an in-phase component. Now you can see here that si of t is nothing but the in-phase component of the bandpass signal, and of s of t, and sq of t is the quadrature phase component of the bandpass signal. Now this implies that if cos 2 pi fct is the multiplying factor of si of t, then it is very viewed as a reference sinusoidal carrier of, then sin 2 pi fct will be the quadrature with respect to the cos 2 pi fct. So what we consider here, the cos 2 pi fct will be having the reference signal, and the sin 2 pi fct will be the quadrature phase, that is a 90 degree shifted. So like that we will be considering. So now in phase component will be accompanied by cos 2 pi fct, and the quadrature phase will become accompanied by the sin 2 pi fct, that is the 90 degree phase shift. According to the equation 10, what we have discussed the previous, the complex envelope s of t may be viewed as the time varying phasor position at the origin of the si of t and si and sq. That is, we can see here si and sq here. So this is the time variant phasor. So when we take for example, for this we can take a resultant, we take a magnitude of the si square plus sq square the whole square, and that is the resultant. How we get this resultant angle, that is sq by si, and we take, when we take a magnitude of this one and we take the tan inverse of this magnitude, so that time we get this kind of the angle, and this is nothing but as a the time varying phasor. And when we take it in terms of the positioning, we can take, you can see it here, this is the real axis and this is the imaginary axis. We take this as a magnitude of 1, and we take this the 2 pi fct in the cos phi, and this 2 pi fct is nothing but the reference of this one. So what we discuss here in this point is been plotted here. So 2 pi fct will be the reference, and that cost will be the in-phase component, and how it is been attained now. And this depicts as a, and the phasor of the complex exponential, that is a j2 pi fct, that is e raised to j2 pi fct. So this is what, with the help of this one, we accompany and we get. Now so this is we got. Now from equation 9 that we have discussed, that the complex envelope s cap of t is being multiplied by the complex exponential e raised to j2 pi fct, and the angle of this two phasors add the length multiply as shown in this figure C. So what I am doing, I am trying to take this one and I am trying to implement here. When they multiply this and this, when we interface it here, so that time what is happening, this what is we have got of sq of t and si of t will be here, and this the magnitude or the what we have plotted, that will be here. So that I multiply and they elongate their length, multiply their length also, this what we have been derived it here, and also the two faces add there. So this angle and this angle get add, and that is the sq, what it was here, again it is little shifted here this way. One will be the reference, this is the reference, and this is the of involving of both the things, the magnitude also and also the multiplication of their length also. You can see it here, si square plus sq of square will be here because of this, and this angle get added and we are getting here. And this one what we have calculated, it has been shown it here. Actually it should have been here, but it has been added here. So this is how we are plotting those things. Now since both si of t and sq of t are low pass signals limited to the band minus w less than or equal to f less than or equal to w, they may be extracted from the band pass signal s of t using the scheme which we have been showing in the next one. So what we have done here, the graphically we will be plotting it to the block diagram, so that we can understand it very easily. Here both the low pass filter are designed identically, each with the bandwidth equal to the W. So they have been assigned with the equal bandwidth of W. To reconstruct S of t from its in phase and the quarter phase component, the scheme has been shown in the 8. So we are getting it back. What we have synthesized and we have been sent, again we are getting it back. So that is the reason for the first one where we analyze all those things, and we have sending this data with respect to the in phase and the quadrature phase is referred as the analyzer, and the one which has to be get back the original data signal, we refer it as a synthesizer. We can see it here. This is the si of t what we will be sending, and we will be passing on to the low pass filter. But before that we will be adding on with the oscillator. So here it is going to multiply with this signal with the si of t, s of t, and we call this one as a si of t, that's the in phase component. Then another which we will be using this one as the in phase component. Then again this same the reference signal, we will be shifting it by the 90 degree, we call it the 90 degree phase shift minus 90 degree phase shifter, and we will be adding all this thing, and we call this one as the quadrature phase component, and we are passing it to the low pass filter. So what we have done the process of that to remove the complex part, and we want only the real part, so that we have analyzed with respect to this block diagram. And this is nothing but the in phase component and a quadrature phase component, so that we are getting it out. So removing the unwanted noise here. Then this we call it as a analyzer. So then again it will pass on to the si of t, and sq of t will be passed on here. Again the same thing, we cancel off the cos 2 pi fct, and we get it back only the si of t here. Again we minus 90 degree phase shift, what we have multiplied, that we have to get done it again here, multiply and get the, and since sin 2 pi fct will be cancelled, which is the carrier for the quadrature phase here, and we get sq of t, and both si of t and sq of t add, and we get a s of t, and this we call it, we synthesize the data back again. Now this is how we are expressing the data send scheme for deriving the in phase and quadrature phase, and reconstructing the band phase signal to get back the in phase and the quadrature phase component. This is all about the canonical representation. Now we look into the polar representation of the band pass signal. The equation s cap of t is equal to si of t plus j sq of t, defining the complex envelope of band pass signal s of t, can be expressed in polar form as s cap of t is equals to a of t into exponential of j pi of t. So here a of t and pi of t are real valued low pass functions. So this is what we are trying to check, that the magnitude of this one we have to represent it here, the angle which they are represented pi of t. Now s of t is equals to real part of s cap of t into exponential of j e raised to j 2 pi fct. That is, we are representing this thing here. That is real part of a of t into exponential of j pi of t into exponential of j 2 pi fct. When we add those things, that we represent the exponential that in terms of e, real part of a of t into e raised to j into 2 pi fct plus pi of t. Now we can represent this one a of t into cos 2 pi fct plus pi of t, as we are referring only to taking the real part. We refer a of t as a natural envelope or a envelope of a bandpass signal s of t, and pi of t as a pace of the signal. So a of t is what now? Only the magnitude of this one, and we consider that one as a natural envelope. So natural, the magnitude it will be there, or the envelope of the bandpass signal. So what is trying to say? It is acting as a one kind of a layers like this way. So what we are trying to say, we are setting up to a one level there a of t, one level it might be some kind of another signal, so which is having that message signal is will be considered as the a of t here. Next, the relationship between the Cartesian and a polar representation of a band pass signal. The envelope, that is the natural envelope a of t, and a phase pi t of a bandpass signal s of t are respectively related to the in phase and a quadrature phase components si of t and sq of t as follows. That is, as I said, a of t is nothing but the square root of si square of t plus sq square of t. Okay, then the phase, that is pi of t, is nothing but tan inverse of sq of t and si of t. So here we are representing the in phase and the quadrature phase component to get a natural envelope, that's the magnitude, or we say it's a normal envelope, and also the angle, also the angle here. Now also we can write this one, the above one, that si of t also we can represent it in terms of a of t into cos pi of t, and sq of t is equals to a of t and sin pi of t. So what we are doing, the natural envelope has been combined with the phase, that is the cos pi of t for in phase component, and with the sine of a quadrature phase component. So these are varied by a minus 90 degree. So that is we call as a quadrature phase. And also here this constitute, that is the in phase and the quadrature phase components of this one, usually contain the amplitude and the phase information. So instead of representing the whole part in that kind of the long equation, even we can represent in kind of a this kind of a terms. So we can represent it in the complex form, and also that complex form can be converted and we can get only into the natural envelope. Also we can represent it only in terms of a the natural envelope and the phase there. But what is required here is the main the in phase and the quadrature phase component. With the in phase and the quadrature phase component, we can write it in the separate, and we can see the cos and the sine with respect to here. So this is how we represent a the Cartesian and the polar form, how they are represented here. So this is the representation of a polar form, and it is a Cartesian form, and here we will represent it in the polar form. This is how we represent only the polar. This is the magnitude, and this is only the phase. So when we compare to the complex polar form representation, it's a little different, where we'll be accompanied by some of the component. So here pi of t will give me the value of the in phase component, and here the sine will be accompanied by this value. So that's the difference between these two values. Okay, thank you.